we go. So, last new material today. Yay, last new material today. Very exciting. Yay, you're allowed to be excited about that. I'm excited about that. It's totally fine this semester. Exam, Monday at 8. Regular time, we won't need to sign in early because it's just a test and it'll only take an hour-ish. So that's Monday. Proof notebook is due Friday. Let me know if you have issues uploading the proof notebook. I think I said you had to have a PDF file, but I also don't think I said it as just one. So if you need to upload multiple PDF files, you can. That's fine. Noon, like our standard, regular, normal noon. Questions on the proof notebook? Anything there? Things that you have questions on? Nope. Nope. Okay. My nose is running and go blow it. Hang on 1 second. Otherwise it's gonna irritate me all class period. And I don't know if you can still hear me while I'm yelling, but this is so much easier in the classroom. Okay, homework due today. I have 3 out of the 6 submissions, which is great. That's fantastic. The rest are due at noon. Make sure to get those in for me, please, and thank you. Homework from chapter 13 is due on Monday at noon. So final exam Monday noon, and today will be the very last homework assignment for this semester. Yay. Again, we can go with yay. Yay is allowed. Anything on all of that logistic stuff before we jump into content? Anybody, anything? Okay, cool. And then one more logistic thing. Friday is Whirlwind Tour for the stuff that is going to be covered on Monday's test. So that is chapter 8 and onward. That's where we're going, chapter 8 through the end of chapter 13. All right, lovely. Chapter 13, section 13.2. I find this section fascinating. I'm hoping that you do also. We'll see. It is fun. It is going to make you crabby again, but that's okay. And I just like it. It's a fun way to end the semester. It kind of brings back a whole bunch of stuff and brings stuff together. So section 13.2, countable and uncountable sets. By the way, I should say this also, I'll say more at the end of the class, but one of my friends, I was Zooming with friends last night, and all of them are math professors or high school math teachers, and one of them was saying, yeah, she really dislikes her handwriting on the whiteboard, like with the stylus and everything, so she's been creating slides for her classes, and she said it takes a ton of time. I'm like, yes, of course it takes a ton of time. So thank you for putting up with my handwriting so that I don't have to create slides and take a ton of time in doing this. I don't love my handwriting either, but hopefully it's acceptable enough, so thank you for not having me do slides and saving some time. All right, let's do definitions here. Here we go. First of all, let A be a set. There are 3 things that we can have. So first of all, A is countable if A is finite, or A is countably infinite. That's going to be definition 2. So A is countable. This has 2 possibilities. If A is finite, or if A is countably infinite. And again, I got to define countably infinite for you in the next one, but 2 different possibilities for countable. A is countably infinite. So countably infinite if the cardinality of A is equal to the cardinality of the natural numbers. So that's countably infinite. Cardinality of A is equal to the cardinality of the natural numbers, countably infinite. And then A is uncountable if A is infinite and the cardinality of A is not equal to the cardinality of the natural numbers. So kind of sort of 3 different categories, or we can think of them as 2 different categories either way. We can think of it as countable and uncountable. We could do it as 2 different categories that way, or we could think of it as 3 different categories: finite, countably infinite, and uncountable, or sometimes uncountable is also called uncountably infinite. Sometimes that's the case as well. So we can either say uncountable or uncountably infinite. Either of those works, uncountable or uncountably infinite. All right, let's do some examples based on what we did last time, and then we'll get into the interesting examples today. So obviously the natural numbers are countably infinite. Right? Clearly, they have the same cardinality as the natural numbers. Easy, no big deal, all good there. Integers, this was the one we did last time. We had a bijection between the natural numbers and the integers, right? So the integers are also countably infinite. That was from last time. We said that there are exactly as many positive integers as there are integers. You didn't like that, and that's okay. It doesn't make sense if you logically think about it, but it's true. Countably infinite. Same thing with the even integers. Remember, if I put a 2 out in front, that's the even integers. Even integers are also countably infinite. And that bijection we proved last time, right? We proved that the size of the integers and the size of the even integers was the same. So again, the statement doesn't make sense, but it's true. There are exactly as many integers as there are even integers, exactly as many. And then the other one we did last time was the real numbers, and those are going to be uncountably infinite. Because we did Cantor's diagonal argument, right? We tried to make a new real number, and we showed that there was no bijection between the integers and the real numbers. We tried to have a bijection, and then we came up with a problem. We did proof by contradiction. Give me a thumbs up that you remember all of these from last time, or not at me or something like that. Good. Okay, so there's a little bit of notation here also. So here's my notation. We've done a lot of Greek this semester, right? We're gonna get Hebrew today. So the notation for the cardinality of the natural numbers, and that's also going to be the cardinality of the integers and the cardinality of the even integers, right? Because all of those sets have the same cardinality, but mostly the cardinality of the natural numbers. I haven't tried drawing this on the whiteboard, and I have a hard time drawing it on a chalkboard anyway, so this is maybe gonna turn out horrible. It's a Hebrew letter, so do a slash from top left to bottom right, and then go the other direction. Oh, that's not too bad. And kind of make it curved. This should end at the same line. This one isn't necessarily any longer than that one. It just kind of ended up that way on my whiteboard. And then it gets a subscript of 0. So this is called Aleph Not. Aleph Not. Okay, that's my symbol. Aleph is Hebrew. That's the first letter of the Hebrew alphabet. I think it's the first letter of the Hebrew alphabet. First letter of the Hebrew alphabet. I have no idea why we are using Hebrew letters for the size of countably infinite sets, but we do, and this is very, very standard across math. Totally and completely standard. So if you talk about Aleph Not, this is absolutely something that a mathematician is going to understand. I'm not making this up. The book is not making this up. This isn't weird notation that this book chooses. This is very, very standard across math, Aleph Not. So what this also tells us is that the cardinality of the real numbers is not equal to Aleph Not. That one wasn't quite so good. We'll get better at Aleph Not. So the cardinality of the real numbers is not equal to Aleph Not, right? Because we know that the cardinality of the real numbers and the cardinality of the natural numbers are not the same. Okay, we've got our sets here. We've got the natural numbers. We've got the integers. We've got the real numbers. We are missing a set in the middle. Yes, we've dealt with another set this semester. We have dealt with the rational numbers, that is Q, and I don't know, well, you do if you read the book, but I don't know at this point in time whether Q is countably infinite or uncountably infinite. So that's the question that we want to answer today. Which is Q going to fall into? Countably infinite or uncountably infinite? That's what we're looking to answer. And I need a theorem first. This will make life a little bit easier. And then we'll do this fun snake argument. So here's my question. Is Q countably infinite or uncountably infinite? That's the question that we want to answer. That's kind of the big set that we have left, is Q countably infinite or uncountably infinite. We need a theorem first. So theorem 13.3, here's my hypothesis. A is an infinite set. So we have an infinite set, and my conclusion is that A is countable if and only if the elements of A can be arranged in an infinite list. So A is countable if and only if the elements of A can be arranged in an infinite list. And we'll notate that list by little a1, little a2, little a3, etc. So A is countable or countably infinite, we can say it either way, if and only if the elements of A can be arranged in an infinite list. Remember what we had last time, right? A set is countable if there's a bijection between the natural numbers and that set. Yes, right? That was our definition from last time, bijection between the natural numbers and that set. We can come up with a bijection. So here's my bijection, F from the natural numbers to that set A. So I'm going to take as input an element X, and I'm going to send it to A sub X. So 1 is going to get sent to A1, 2 is going to get sent to A2, 3 is going to get sent to A3, etc. And that's the proof of the theorem. I could write it out as a proof if I really, really wanted to, but that's where your bijection is coming from. So a bijection with 1 going to something and 2 going to something and 3 going to something is basically the same as writing out the elements in an infinite list. Do you kind of sort of see why that's true? Why I have a bijection there if I write these out in an infinite list? That makes sense, kind of, sort of? Okay, so that's the basic proof. The book may or may not have a proof, I'm not sure, but that's the basic proof that you want. All right, so then, for example, my infinite list for the natural numbers is easy. That's just gonna be 1, 2, 3, 4, etc. So that tells me the natural numbers are countable. No big deal there. My infinite list for the integers, we could go 0, 1, -1, 2, -2, 3, -3, etc. Easy, no big deal there. We've got an infinite list, that's all good. For the even integers, we could do 0, 2, -2, 4, -4, etc. So we can make infinite lists for all of these. All good, that means all of these are countable. That backs up what we did last time. All right? Hanging with me? So far, so good? Everybody good? Okay. All right. So then what we want is to answer our question.